are going to explore momentum. What is this momentum that we hear about? Momentum is probably a term you've heard in terms of football. This player has a lot of momentum as you knock the other guy over. So momentum is basically also looked upon as mass in motion. How much mass is in motion. Simply put, momentum, we use the letter P. Why? Probably because it was the only letter left over, or one of the few letters left over that we could use, is equal to mass times velocity. So it's a product of the mass and the velocity. Mass, if you know, is the amount of matter that something has, and velocity is the speed with a certain direction. So since velocity is a vector as we know it to be versus a scalar quantity like speed, then momentum is also going to be a vector because we have a scalar times a vector, which gives us a vector, meaning that we can describe it in terms of an arrow where the length of the arrow tells us how much, and the direction is of course the direction in which the arrow is pointing. And just like we added momentum, or like we added forces or displacement by adding the arrows, if we had a displacement in this direction of this quantity, another one in this quantity of this direction, then the net displacement is presented by this dotted arrow there. Similarly, momentum would be added in the same way, geometrically versus arithmetically, like we would normally add a scalar quantity. The units for momentum, as the product itself goes, is mass is in kg and velocity is in meters per second, giving us units of kgms. Unfortunately, there's no shortcut unit for this, like Newton is kilograms meters per second square. For momentum, we just use kgms. So to calculate momentum is really straightforward. It's just the product of the mass and the velocity. So let's assume we have a car that's moving to the right, the velocity of 5 meters per second. It has a mass of 1,000 kg. So the momentum, which is mass times velocity, would simply be 1,000 kg times 5 meters per second, which gives me 5,000 kgms. And so that would state that this car has a momentum of 5,000 kgms. Similarly, if that same car was now traveling towards the left with a velocity of, or a speed of 5 meters per second, meaning it has a velocity of negative 5 meters per second, then our momentum would be 1,000 kg times negative 5 meters per second, giving us negative 5,000 kgms. Start with another simple question. We have a car, 1,000 kg car, moving to the right at 22 meters per second. What is its momentum? Again, P equals mv, and our momentum would be 1,000 kg times 22 meters per second, which gives me 22,000 kgms. Really, really, really straightforward. Let's look at another question. In this case, we have a 1.2 kg ball traveling towards the left at 4 meters per second. Again, P would be mv, which is 1.2 kg times negative 4 meters per second. It's really important that we pay attention to left and right, or up and down, when we're looking at momentum. And so that would give us negative 4.8 kgms. Okay. Next, let's see. A bowling ball of mass 3.5 kg moves in a straight line at 1.4 meters per second. How fast must a ping pong ball of mass 2 grams move in the same direction so the two balls have the same momentum? Alright, so let's figure out what is the momentum of the bowling ball. so we can set this equal to the same thing. The momentum of the bowling ball, I'll call it PB, is equal to the mass of B times the velocity of B, which is our bowling ball. So we have 3.5 kg times 1.4 meters per second. And when we put that in our calculator, we get 3.5 times 1.4, which is 4.9 kgms. Now we want our little ping pong ball to have that same momentum. So we want the momentum of the ping pong ball, I'll call it P. We want that also to equal to 4.9 kgms. So we say, okay, this must equal to the mass of the ping pong ball times the velocity of the ping pong ball, which means that 4.9 kgms must equal to the mass of the ping pong ball. Since we're doing this in kg, we'll move this in kg as well, be 0.002 times the velocity, which is what we're looking for. So then the velocity of the ping pong ball, again, what I'm doing here is I'm going to divide both sides by 0.002 to make sure that I get VP by itself. And so now I look and I see that VP would be 4.9 divided by 0.002, which gives me 2450 meters per second. Now that's a super high speed, faster than the speed of sound. So that's how fast that little ping pong ball would need to move to have the same momentum as the bowling ball. So when I multiply this new velocity, which is the new ping pong ball, it is 0.003 or 2, sorry, times 2450 meters per second, which should give me 4.9 kgms. Okay, so pretty straightforward, pretty much using the same equation in each case, and this was of course a simple case where both were moving in the same direction. We didn't need to worry about the sign or any of those things. Alright, now we have a 2 kg object moving with a velocity of 6 meters per second to the right, while a 4 kg object is also moving to the right at 3 meters per second. Find the total momentum of the system. Now this term system, you need to kind of get used to it. Basically, when I think of system, I think of a system that is like, I just pretend that these are the only two things in the entire universe. There's nothing else. Nothing else is going to bother it, interact with it. It's just going to be these two guys, pretend they're drifting out in space and it's just them. That makes it a little easier to kind of look at what we mean by a system. And it's just these two objects and nothing else but them. And so if I were to find the momentum of both of these together, I'd simply be adding the two momentas. So P total would be PA plus PB, momentum of A and the momentum of B. Since they're both moving in the same direction, they will be adding. So we have 2 kg times 6 meters per second for A plus 4 kg times 3 meters per second for B. That gives me 12 kg ms plus 12 kg ms, giving me 24 kg ms. So what we're stating here is that the momentum of both these guys together, considering this to be a system, so we pretend this is like one big object, that their momentum combined is 24 kgms, and we'll see shortly why do we care about adding the momentum of two of these guys together. And this will lead us to an important concept in momentum that we will look at that'll help us solve problems for when these two guys do collide with each other and we want to predict what is the aftermath of that collision. But right at this point we'll just look at, how do we find the momentum of a system or of two objects combined together. Next we look at a similar system, but here now we have B is coming in the opposite direction, so if I had to write the momentum of A, PA would be 25 times 3, or 75 kgms. And the 15 kg object, that's this guy here, I'll just put these in here, and that's 25 kg. The 15 kg object is moving to the left, so PB would equal to 15 times negative 4 meters per second, which would give us negative 60 kgms. So now when I want to find the total momentum, I'll call it PT, will be PA plus PB, and in this case it would be 75 kgms plus a negative 60 kgms, giving you 15 kgms. And since this is positive, we know that the total momentum of both these guys is pointing to the right. Basically it has a net momentum that acts in that direction. And so what we'll find later is we will apply conservation of momentum, the topic we're going to learn next. And this allows us to predict that even if this is a closed system and there are no external forces, then even after they were to collide and maybe they stick together, maybe they move apart in different directions, maybe they're both moving towards the right, but the total will still be 15 kgms afterwards, and that's something we're going to look at. So at this point we're just seeing how do we calculate the momentum of a system, and there are two objects. We simply add them together, and just like because they're vectors, we got to pay attention to the direction. And one last case here. What if I had more than two objects? What if I had 3 or even 100 objects? It's the same process. I'll call this P1, P2, and P3, and so P total will simply be the sum of P1 plus P2 plus P3. P1 in this case is 2 times negative 3 meters per second, and that gives you negative 6 kgms. And then we look at P2, which is 5 kg times 2 meters per second, or 10 kgms. And so that's P2 is 10 kgms, and then P3 is 5 and 1, which gives us, that'd be negative 5, and so it'd be negative 5 kgms. So when I add them all together, I have negative 6 plus 10 minus 5, which gives me negative 1 kgms. And again, the negative 1 here is simply implying that the total momentum of this whole system is pointing to the left. If you recall from Newton's first law that a velocity of an object will remain constant unless acted upon by an external force, we could extend that further to a system of objects, which is all of these together, and their momentum will remain constant even after they collide or whatever else would happen, as long as there are no external forces. it's a wrap up for now, and we will see you again on the next video. Bye for now.
Thank you for watching. If you liked the video or found it helpful, please like us.